The ground beneath the sprawling industrial complex of Khimki, just north of Moscow, does not merely shake when the engineers at NPO Energomash ignite their creations. It convulses with a violence that registers on seismographs miles away. This is not the clean, sterile silence of a computer laboratory, nor is it the hum of a modern assembly line, but rather the guttural roar of a chained beast fighting against its bonds. Here, in the heart of the Russian aerospace industry, lies a legacy forged in the paranoid desperation of the Cold War and refined into the most formidable liquid propellant rocket engines ever constructed by human hands. We are standing at the perimeter of a test stand that looks less like a piece of scientific equipment and more like a concrete fortress designed to withstand a nuclear siege, which is fitting because the forces unleashed inside are barely contained thermonuclear energies in terms of raw heat and pressure. The story of this facility is not just a tale of metal and fuel, but a saga of hubris, metallurgical alchemy, and a refusal to accept the limits of physics. To understand the sheer magnitude of what happens inside the walls of Energomash, you must first strip away the romanticized image of spaceflight as a graceful ascent into the stars. A rocket launch is a controlled explosion, a continuous detonation that is being forced through a throat of metal, and nowhere is that detonation more violent, more efficient, or more terrifying than inside the combustion chambers of the RD-170 and its direct descendant, the RD-180. These engines are the pinnacle of what is known as oxygen-rich staged combustion, a technology that American engineers once declared impossible, believing that any attempt to build it would result in the engine simply eating itself alive. Yet, deep within this Russian factory, amidst the smell of heavy machine oil and the flickering fluorescent lights of Soviet-era assembly halls, they not only built it, they perfected it. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming, because the story of how we leave this planet is written in steel, fire, and the sweat of machinists. The central conflict of this engineering marvel lies in the fundamental chemistry of burning kerosene and liquid oxygen. In a standard rocket engine, you have a massive pump that shoves fuel and oxidizer into the main chamber. But that pump needs a power source, usually a smaller turbine, to spin it. In traditional Western designs, like the ones that took Apollo to the moon, the exhaust from that smaller turbine was dumped overboard, wasted, and lost to the atmosphere, which is somewhat like driving a high-performance sports car but pouring 10% of your gasoline onto the asphalt every mile, just to keep the fuel pump running. The engineers at Energomash, led by the legendary and uncompromising Valentin Glushko, looked at that wasted fuel and saw an offense against efficiency that they could not abide. They decided to feed that exhaust back into the main engine to squeeze every ounce of thrust from the propellant, creating a closed loop where nothing is wasted. However, doing this required a decision that would haunt metallurgists for decades. To make the cycle work, Glushko decided to pump all of the liquid oxygen through the preburner first, creating a screeching, superheated tornado of oxygen gas that would then drive the turbines. This is where the nightmare begins for the materials engineer. Hot, high-pressure oxygen is not just a gas, it is a ravenous predator that wants to chemically bond with and incinerate almost everything it touches, including the metal walls of the engine itself. Imagine trying to build a fireplace where the bricks themselves are made of compressed wood, and you are trying to keep the fire contained without the structure burning down around you. That is the challenge of the oxygen-rich pre-burner. It is a balancing act so precarious that for years, Western observers simply refused to believe the Soviets had solved it, assuming the intelligence reports were exaggerated. Before we descend into the inferno of the combustion chamber, let the mind rest for a moment in the deceptive quiet of the assembly floor at Energomash. It is a vast cathedral-like space where the ceiling is lost in shadow and the floor is a patchwork of heavy steel plates and worn concrete. There is a specific smell here, a mixture of ozone, unburnt kerosene, and the metallic tang of grinding dust that hangs in the air like a permanent fog. The light filtering through the high windows catches the dust motes dancing in the silence, a stillness that feels heavy, almost oppressive, because everyone walking these floors knows that the sculptures of steel sitting on the trestles are waiting to scream. The solution to the oxygen problem required a dive into the molecular structure of the alloys themselves. The engineers at Energomash could not simply use standard stainless steel or even high-grade Inconel, because under the pressure of 250 atmospheres and temperatures soaring past 500 degrees Celsius, those metals would ignite and burn as readily as paper in a blast furnace. They had to develop proprietary superalloys, specific blends of nickel, chromium, and exotic trace elements that could withstand the assault. But the alloy alone was not enough. The brilliance of the design lay in the creation of a protective oxide layer, a microscopic skin of rust that formed on the inside of the pipes. Think of this protective layer like the enamel on your teeth. It is incredibly hard, remarkably thin, and it is the only thing standing between the soft, vulnerable core and the destructive environment outside. If that oxide layer cracks or flakes off due to vibration or thermal shock, the oxygen will attack the exposed fresh metal instantly. The result is what engineers call a burn-through, but that clinical term fails to capture the horror of a catastrophic engine failure where the high-pressure gas acts like a plasma cutter, slicing through inches of steel in a fraction of a second and turning the entire engine into a bomb. The discipline required to manufacture these components is absolute. A single fingerprint, a stray fiber from a cleaning cloth, or a microscopic scratch on the inner wall of the oxygen manifold can create a friction point that triggers ignition. The workers assembling these beasts are not just mechanics. They are more akin to surgeons operating in a clean room, yet dealing with components that weigh as much as a small car. Now consider the turbopump, the beating heart of the RD-170 family. This single piece of machinery is a feat of engineering so dense with power that it defies easy comprehension. To move the sheer volume of fuel and oxidizer required to lift a rocket, the shaft of this pump must spin at incredible speeds, generating nearly 200,000 horsepower. To put that into perspective, imagine the engine power of the entire starting grid of a Formula One race, plus the reserve cars, and compress all of that energy into a device that is roughly the size of a refrigerator. The shaft connecting the turbine to the pumps transmits this colossal torque while enduring thermal gradients that would snap a lesser material in half. On one end of the shaft, you have the liquid oxygen pump, chilled to hundreds of degrees below zero. A few feet away, the turbine is glowing red hot from the pre-burner exhaust. The thermal shock across the turbopump shaft is equivalent to taking a thick glass rod, dipping one end in liquid nitrogen, and holding a blowtorch to the other end, all while twisting it with the force of a freight train. The fact that the shaft does not shatter is a testament to the specialized manufacturing processes developed at Energomash. They utilize a complex system of seals and helium purges to keep the volatile fluids apart, because if the kerosene and the liquid oxygen were to meet inside the pump machinery rather than in the combustion chamber, the resulting detonation would erase the test stand and anyone unfortunate enough to be near it. The tolerances here are measured in microns, forcing machinists to account for the thermal expansion of the metal, knowing that a gap that is perfect at room temperature might bind and seize once the superheated gas begins to flow. Let us step back from the terrifying precision of the turbopump and feel the atmosphere of the facility during the winter. Outside the heavy brick walls, the Russian winter buries the industrial park in a blanket of white, muting the sounds of the city. The air is crisp and painful to breathe, contrasting sharply with the sweltering heat radiating from the heat treatment furnaces inside. There is a palpable sense of history in these corridors, a ghostly presence of the thousands of engineers who spent their lives chasing a specific vision of perfection. You can see it in the worn handles of the heavy steel doors and the faded instructional posters on the walls, relics of an era where the space race was a matter of national survival. The combustion chamber itself is where the final act of this violent ballet takes place. In the RD-170 and RD-180, the fuel and oxidizer meet at pressures that are almost incomprehensible, over 3,700 pounds per square inch. At these pressures, the fluid dynamics change. The propellant doesn't just burn, it behaves more like a detonating explosive that is continuously being fed. The walls of the combustion chamber must survive temperatures that exceed 3,000 degrees Celsius, which is hot enough to boil steel into a vapor. To prevent the engine from melting, Energomash utilizes a technique called regenerative cooling. Imagine the combustion chamber not as a solid metal cone, but as a sandwich of inner and outer linings. Between these linings, milled into the copper alloy of the inner wall, are hundreds of tiny channels. Before the kerosene is injected into the engine to be burned, it is first raced through these channels at high speed, absorbing the heat from the combustion chamber wall. This serves a dual purpose. It keeps the copper from melting, and it preheats the fuel, making it burn more efficiently when it finally reaches the injector. It is the same principle as a radiator in your car, but instead of air cooling water, you are using the rocket fuel itself to cool the engine, dancing on the knife edge of boiling the fuel in the pipes. If the fuel boils before it exits the cooling channels, it creates gas bubbles that block the flow of liquid, leading to a hot spot and, inevitably, a catastrophic melt-through. The manufacturing of the inner liner involves a copper-chromium alloy that provides high thermal conductivity, allowing the heat to pass through to the coolant as fast as possible. But copper is soft, and the pressures inside the engine are enormous. To keep the copper liner from bulging or bursting, it is reinforced by a structural jacket of high-strength steel. Joining these two disparate metals, the copper liner and the steel jacket, requires a brazing process of immense complexity. The entire assembly is placed in a vacuum furnace and heated until a thin layer of gold palladium or similar brazing alloy melts and fuses the two shells together. If there is a single gap in that braze, a single bubble of air trapped between the layers, the heat transfer will fail at that spot, and the engine will destroy itself in milliseconds. We must now confront the operational reality of building these monsters. It is one thing to design an engine on paper. It is another to cast the metal, machine the surfaces, and assemble the thousands of components required to make it work. The foundry at Energomash is a place of smoke and fire, where molten alloys are poured into ceramic molds with a precision that borders on the artistic. Casting defects are the enemy. A microscopic void, a tiny pocket of air trapped inside a turbine blade, acts as a stress concentrator. When that blade spins up to speed, the centrifugal forces pulling on it are immense, tens of thousands of times the force of gravity. That tiny void becomes a crack. The crack propagates, and suddenly the blade disintegrates, sending shrapnel through the engine like a grenade going off in a crowded room. Knowing what you now know about its real-world production bottlenecks, the extreme hazards of oxygen-rich combustion, and the constant threat of catastrophic failure, do you think the massive capital investment in this facility and this complex technology was worth it compared to simpler, safer designs? Share your thoughts below, because the trade-off between raw efficiency and manufacturing nightmare is the central debate of rocket science. The testing phase, known as the green run, is where the rubber meets the road, or rather, where the fire meets the deflector plate. When an RD-180 is strapped to the test stand at Energomash, the preparation takes days. The engine is instrumented with hundreds of sensors, measuring pressures, temperatures, and vibration frequencies. The propellant lines are chilled down, a process that causes the pipes to groan and contract as liquid oxygen at -183 degrees Celsius flows through them. Frost forms inches thick on the outside of the valves, shedding like snow when the system is jolted. The technicians retreat to the blockhouse, a bunker with walls of reinforced concrete several feet thick, and the countdown begins. When the ignition command is given, the world outside the blockhouse effectively ends. The sound is not something you hear, it is something you survive. It is a physical pressure wave that hits the chest and vibrates the fluid in your eyes, blurring your vision. The low-frequency acoustic energy is so intense that it can heat the air through friction alone. On the flame trench, hundreds of tons of water are dumped per second to suppress the noise and cool the exhaust, instantly flashing into a cloud of steam that rises like a mushroom cloud over the facility. For the engineers watching the monitors, the tension is excruciating. They are watching the pressure curves, looking for the slightest anomaly, the tiniest flutter in the turbopump speed that might indicate a bearing is about to seize, or a seal is about to give way. The logistics of moving these engines are a saga in themselves. The RD-170 is a four-chambered Leviathan that is roughly the width of a bus. Transporting it from the assembly hall to the test stand and eventually to the launch site requires custom-built railcars and heavy-lift cranes. The engine is so heavy that its own weight could deform the delicate nozzle extensions if it were simply set down on the floor. It must be cradled in a specialized transport frame that supports it at specific hard points, distributing the load to prevent the copper linings from warping. The journey from the factory gate in Khimki to the launch pads at Baikonur or Plesetsk, or the shipping docks for export to the United States, is a slow, careful procession, ensuring that the precision alignment achieved in the factory is not undone by a pothole in the road. There is a human cost to this level of heavy industry. The men and women who built Energomash worked in an environment that was, by modern standards, hazardous in the extreme. In the early days, safety protocols were often secondary to the schedule. Exposure to toxic chemicals, the constant assault on the eardrums from engine tests, and the psychological pressure of failure in a state-run economy took a heavy toll. Yet, speaking to the veterans of the plant, you find a fierce, almost religious pride. They speak of the engines not as machines, but as living things with personalities. They know which test stand produces the best data, which batch of alloy was troublesome to machine, and which specific engine number gave them sleepless nights. The silence that follows a test firing is perhaps the most profound sound at Energomash. As the echoes die away and the steam cloud begins to dissipate, the cooling systems continue to hiss, spraying water on the scorched metal of the test stand. The engine itself ticks and pings as it cools, the metal contracting back to its resting state. The smell of kerosene is everywhere, coating the back of the throat. For the engineers, this is the moment of truth. They emerge from the bunker to inspect the hardware, looking for discoloration, leaks, or cracks. A successful test means the engine is certified for flight. A failure means months of investigation, forensic analysis of the wreckage, and the sinking feeling that they missed something in the thousands of steps leading up to this moment. Now we must assess the legacy of this industrial titan. The RD-180, a two-chambered derivative of the original four-chambered monster, became the workhorse of the American Atlas V rocket. It is one of the great ironies of the post-Cold War era that the engines designed to launch Soviet intercontinental ballistic missiles ended up launching American spy satellites and scientific probes to Mars. The American aerospace giants, for all their prowess, found that it was cheaper and more reliable to buy these high-performance engines from Russia than to replicate the terrifying complexity of the oxygen-rich staged combustion cycle themselves. It was an admission that, in this specific niche of metallurgy and fluid dynamics, the engineers at Khimki had achieved something unique. However, the dominance of the RD-180 is not just about raw power, it is about the philosophy of robustness. Western engineering often prioritizes lightweight, elegant solutions that operate right at the margin of safety to save weight. The Russian philosophy, embodied by Energomash, is different. They build heavy, they build strong, and they accept the weight penalty in exchange for an engine that can tolerate a wider range of operating conditions. The turbopumps are overbuilt, the combustion chambers are thicker, and the safety margins are wider. It is the difference between a high-strung race car engine that needs a rebuild after every race and a heavy-duty diesel generator that will run for 10 years without complaint. Yet, no machine is perfect, and the reliance on such complex plumbing brings its own risks. The nested loops of the staged combustion cycle mean that a problem in one part of the engine instantly propagates to the rest. If the pre-burner runs slightly too hot, the turbine blades soften. If the turbine slows down, the pumps lose pressure. If the pressure drops, the cooling flow to the nozzle decreases. If the cooling fails, the engine melts. It is a feedback loop of destruction that can happen faster than a human can blink. The automated control systems designed to catch these failures are marvels of electronic logic, reacting in milliseconds to shut down the valves before the engine can disassemble itself. But even they cannot always beat the physics of a high-pressure burn-through. The legacy of NPO Energomash is etched into the history of spaceflight. They demonstrated that the impossible oxygen-rich cycle was not only possible, but could be the basis for the most reliable engines in the world. They turned the terrifying chemistry of hot oxygen and metal into a manageable industrial process. Walking through the facility today, you see the juxtaposition of the old and the new. Modern CNC machines sitting next to manual lathes that turned parts for the Soviet moon rocket. It is a place where the ghosts of the past are very much alive, guiding the hands of the new generation as they weld the arteries of rockets that will carry humanity further into the void. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching. The story of heavy industry is often one of brute force, but at NPO Energomash, it is a story of brute force controlled with the precision of a watchmaker. It reminds us that the path to the stars is paved with difficult choices, dangerous materials, and the audacity to contain the fire that Prometheus stole, even if it threatens to burn the hands that hold it. The silence returns to Khimki, but the ground remembers the shaking, and deep in the metal of the test stands, the vibration waits for the next command to ignite.